a galaxy so large that the Milky Way would seem almost like a small lantern. Beside it sits far away in the heart of Abel, 2029. Its name is IC1101, a colossal red giant possibly stretching 6 million light-years across, holding the faded light of up to 100 trillion stars and hiding a dark engine at its centre that may be among the most massive black holes ever suspected. This is not just a story about size, it is a story about time, collision, silence, and the slow aging of the universe itself. Welcome to Boring Science Stories. Thank you for spending part of your day or night here with us. If this calm journey into deep space helps you relax, please leave a like, subscribe, and share it with someone who loves quiet cosmic mysteries. Also, tell us in the comments what time it is for you and where you're watching or listening from. Now, drift with us into the largest galaxy ever found. Across the observable universe, galaxies are the great cities of light, each one a broad gravitational gathering of stars, gas, dust, dark matter, and time. They do not sit in space as simple ornaments, scattered at random in a silent dark. They form a web. They gather in pairs, groups, clusters, and immense superclusters, linked by gravity into patterns so large that even light needs millions and billions of years to cross them. Some are small enough to seem almost fragile, faint knots of old stars drifting beside larger companions. Others are grand spiral systems, wide and luminous, turning slowly with arms of blue star-forming regions wrapped around ancient golden centres. And then there are the giants, galaxies so large and old that their shapes have softened, their arms have vanished, and their histories are written not in delicate patterns, but in sheer scale. IC1101 belongs to this last and most imposing family. It is not merely a large galaxy in the ordinary sense. It is one of the most extreme galactic systems known, a vast elliptical presence in deep space whose reported size has made it a symbol of cosmic excess, a reminder that the universe can build structures far beyond the scale of any familiar night sky. The story begins not with IC1101 alone, but with the larger population from which it emerged. Modern astronomy suggests that the observable universe may contain not merely hundreds of billions of galaxies, but perhaps as many as 2 trillion, depending on how faint and distant a galaxy can be counted. Most of these are not the bright, graceful spirals that dominate popular images of space. Many are small, dim, ancient, or far beyond the reach of easy observation. Some are nearly lost in the background glow of the early universe. Some are stretched and distorted by gravitational encounters. Some are only detected because their stars, gas, or central black holes leave subtle traces in the light that reaches Earth after immense journeys through space. To speak of galaxies as a population is already to speak in almost impossible numbers, because each galaxy contains its own population of stars, and many of those stars may have planets, moons, asteroids, comets, magnetic storms, frozen worlds, dead worlds, and perhaps in rare cases living worlds. A single galaxy can be a universe of environments. A cluster of galaxies can contain thousands of such universes in miniature, all moving through a shared field of gravity. Over roughly 13 billion years of cosmic history, galaxies have formed, collided, merged, faded, revived, and transformed. They are not fixed objects. They are events stretched across time. In the early universe, gravity worked on small irregular clumps of matter, drawing gas into denser regions where the first stars could ignite. The first galaxies were likely smaller and more chaotic than the mature systems seen nearby today. They were fed by streams of primordial gas. Their stars lived hard and quickly. Their explosions enriched space with heavier elements. Their central black holes, when present, may have grown rapidly, shaping the gas around them and helping determine whether future generations of stars could form. From these beginnings, galaxies became larger through accumulation. Small systems were pulled into larger ones. Dwarf galaxies fell into spirals. Spirals collided with other spirals. Groups settled into clusters. At every scale, gravity acted as both architect and destroyer, building grander structures by disrupting smaller ones. This is why the largest galaxies are rarely isolated. They're usually found in places where the universe has provided them with many neighbours, many opportunities for collision, and enough time for one object to become the dominant centre of a crowded region. IC1101 sits in such an environment. It lies around 1 billion light-years from Earth, at the heart of the galaxy cluster Abell 2029. A galaxy cluster is not just a collection of galaxies placed near one another. It is a vast gravitational system, filled not only with galaxies but also with hot thin gas and dark matter, a surrounding structure that may weigh far more than all its visible stars combined. In such clusters, the central region becomes a place of slow gathering. Over billions of years, massive galaxies can sink toward the middle through gravitational interactions. Smaller systems can be stripped of stars. Large galaxies can merge again and again, their outer halos expanding, their shapes becoming smoother, their colours growing older. The brightest galaxy near the centre of a cluster often becomes a special kind of giant, sometimes called a brightest cluster galaxy. These galaxies are not simply born large, they are assembled. Their scale is a record of their environment, and their light is a fossil of many swallowed histories. IC1101 is one of the most famous examples of this cosmic process. Its reputation comes from its extraordinary reported dimensions, sometimes described as reaching around 6 million light-years across, with an enormous stellar population that has been estimated in the tens or even hundreds of trillions. Such numbers place it in a realm where ordinary comparison begins to lose its power. The Milky Way itself is vast, a barred spiral galaxy containing hundreds of billions of stars and spanning well over 100,000 light-years in its bright stellar disk, with a still larger halo beyond. To cross it at the speed of light would require more than 100,000 years. Yet IC1101, by some estimates, extends so far that the Milky Way would appear modest beside it, not as a twin but as a lesser structure within a far broader glow. Even this comparison must be handled carefully, because galaxies do not have hard edges. A planet has a surface. A star has a visible boundary where its light thins into space. A galaxy fades gradually. Its outer stars become more scattered. Its halo blends into intergalactic space. Its dark matter may extend far beyond what telescopes can easily trace. For a galaxy like IC1101, the question of size is therefore also a question of definition. Is the diameter measured by bright visible starlight, by faint outer halos, by gravitational influence, or by the broadest possible distribution of associated stars? The more enormous the galaxy, the more delicate the boundary becomes. Still, even with caution, IC1101 remains an object of exceptional scale. It represents the upper reaches of known galactic growth, where repeated mergers have erased the features of youth and replaced them with an immense, smooth, aging radiance. The contrast with a young spiral galaxy is striking. A spiral is filled with structure. Its arms hold clouds of gas and dust where new stars are born. Blue stars burn hot and briefly, marking active regions like sparks along curved lanes. An elliptical galaxy, especially a giant elliptical, is different. It often contains older stars and much less cold gas. It does not show the same clear arms or bright nurseries. Its light tends toward yellow, orange, or red. Not because it is cold in any ordinary sense, but because many of its young blue stars have already died, leaving longer-lived, older populations behind. In this way, a galaxy can carry its age in its colour. IC1101 is not a place of youthful spiral motion. It is a galaxy shaped by the aftermath of many encounters, a settled relic of violence made quiet by time, yet quiet does not mean simple. At its centre there is likely a tremendous black hole, perhaps an ultramassive one, surrounded by a region where gravity, stars, and hot gas have been shaped by extreme forces. Around it stretches an immense stellar body, not a tidy disk, but a broad elliptical envelope. A luminous memory of older galaxies that once had separate names, separate shapes, and separate futures. The largest galaxies are therefore not only large in space, they are large in history. Each one is a layered archive of collisions. Stars that formed in small early systems may now drift inside a giant elliptical, carrying the chemistry of a vanished galaxy in their atmospheres. Globular clusters may orbit far from the centre, survivors of ancient assemblies. Streams of stars may be stretched and diluted until only sensitive observations can reveal them. When such a galaxy is seen from Earth, its image may appear calm and featureless, but this smoothness is deceptive. It is the smoothness of something repeatedly mixed. IC1101 is a cosmic city built from many former cities, a central monument in a region where gravity has been collecting matter for most of cosmic time. Its immense scale invites speculation because the mind naturally asks what could exist inside so many stars. It also invites humility, because even the largest known galaxy is only one structure within a universe filled with structures that remain difficult to count, difficult to measure, and sometimes impossible to see directly. Beyond IC1101 there are other giant ellipticals, other clusters, other distant systems whose light has been travelling since long before Earth's present continents took shape. Beyond them lies the cosmic horizon, the limit imposed not by the end of space, but by the age of light and the expansion of the universe. The largest galaxy ever found is therefore not merely a record holder. It is an opening. It stands as a gateway into questions about how galaxies grow, how matter gathers, how black holes influence their surroundings, and how far cosmic scale may continue beyond what current instruments reveal. In the stillness of deep space, IC1101 suggests that the universe is not only vast because it contains many things, it is vast because some of those things have had enough time, gravity, and darkness to become almost unimaginably large. The path from a small galaxy to a giant galaxy is not a simple ladder of size, but a long history of gravity, environment, and survival. Galaxies are often introduced as if they belong to neat families, with dwarfs at one end, spirals in the middle, and ellipticals at the far massive end. This is useful, but it can make them seem more fixed than they truly are. A galaxy is not born with a permanent identity. It changes as gas falls inward, as stars age, as neighbouring galaxies pass close by, and as invisible dark matter guides the movement of everything inside and around it. The smallest galaxies in the universe can be faint and irregular, with only a modest number of stars compared with great spirals. Some dwarf galaxies contain just a few 100 million stars, and some may be even more ghostly, with so little light that their presence is known mainly through the motion of their stars and the pull of unseen mass. They may stretch only a few hundred or a few thousand light-years across in their brightest parts, though their dark matter halos can be broader. These dwarf systems are often ancient, fragile, and easily disturbed. Around the Milky Way, They move like small companions in a larger gravitational kingdom, some still intact, some being pulled apart into streams of stars. Their scale is small by galactic standards, but they are not unimportant. In a universe shaped by growth through merging, dwarf galaxies are among the earliest building blocks. They are the small stones from which later structures may be assembled. In the first generations of cosmic history, matter did not immediately arrange itself into galaxies like the Milky Way or Andromeda. It gathered into smaller clumps, where gas cooled, stars ignited, and gravity began its patient work. These early systems were likely irregular, turbulent, and rich with star formation. Their stars helped alter the universe itself by creating heavier elements inside their cores and spreading them into space through winds and explosions. Over time, some small galaxies remained small, others were swallowed, some lost their gas and became dim relics, some fell into larger halos, where their stars were stripped away and scattered through the outskirts of growing galaxies. In this sense, every large galaxy contains the traces of smaller ones. The Milky Way itself is not a single untouched object, but a layered system shaped by past mergers and continuing interactions. Its halo contains old stars and globular clusters that may have come from absorbed dwarf galaxies. Its disk still holds gas and active star-forming regions, while its centre carries the mass of older populations and a central black hole. It is a spiral galaxy, a broad rotating system where structure is clearly visible. Spiral galaxies are among the most visually recognizable objects in astronomy because their shapes reveal motion, density waves, and the ongoing cycling of matter into new stars. Their arms are not solid material arms like the arms of a wheel. They are regions where gas and stars pass through patterns of higher density, where clouds can compress, where blue young stars briefly shine, and where dark lanes of dust trace the raw material of future suns. A spiral galaxy is therefore both an old system and a living system. It may contain very ancient stars in its halo and bulge, while at the same time forming new stars in its disk. Its beauty is not merely decorative, it is evidence of balance, with gravity organizing matter into a disk while gas remains available for renewal. The Milky Way belongs to this kind of middle world. It is neither a tiny dwarf nor a giant elliptical. It is large enough to hold hundreds of billions of stars, complex enough to have arms, bars, satellite galaxies, star clusters, molecular clouds, and a broad halo, yet still modest compared with the largest known galaxies. In a spiral like the Milky Way, gas matters deeply. Cold gas is the future. It is the reservoir from which new stars are made. When a galaxy has plenty of it, star formation can continue over immense spans of time. When gas is heated, stripped, consumed, or expelled, the galaxy begins to lose its ability to renew itself. This is one of the key differences between many spirals and many giant ellipticals. Spirals often remain blue in certain regions because they are still producing hot, massive young stars. Ellipticals tend to look yellow, orange, or red because their youngest and hottest stars are mostly gone, and their light is dominated by older, longer-lived stars. The colour is not a decoration laid over the galaxy, it is a clue to its history. A blue galaxy is often still forming stars actively. A red galaxy is often quieter, older, and more gas-poor. Yet even this distinction has exceptions, because galaxies are complicated and their appearance depends on mass, environment, dust, and the details of their past. Still, the broad pattern remains powerful. Dwarf galaxies may be irregular and vulnerable. Spirals may be structured and star-forming. Ellipticals may be smooth, old, and vast. The great ellipticals sit at the end of this progression not because every galaxy inevitably becomes one, but because repeated collisions can transform galaxies in that direction. When two spiral galaxies merge, their disks are disturbed, their arms twist, stretch, and lose their former order. Gas clouds may collide and compress, igniting bursts of star formation. Central black holes may move inward and eventually combine. Stars, because of the enormous distances between them, usually do not collide directly, but their orbits are reshaped. The result can be a larger, smoother galaxy, less like a disk and more like a cloud of stars moving on many different paths. If this happens again and again, the galaxy can become a giant elliptical, with little of its original spiral structure remaining. These galaxies are sometimes called featureless, but that word can be misleading. They may lack arms, bright knots, and dramatic dust lanes, yet they are full of hidden structure. Their outer regions may contain faint shells and streams from past mergers. Their centers may have cores shaped by black hole interactions. Their star populations may preserve chemical clues from many ancestral systems. The apparent simplicity of an elliptical galaxy is often the final calm after a long series of disruptions. The largest ellipticals are especially common near the centers of galaxy clusters, where the density of galaxies is high and mergers are more likely over cosmic time. In these places, a central galaxy can grow by absorbing companions and gathering stars stripped from other cluster members. It may become surrounded by a diffuse halo of light, so extended that it is difficult to decide where the galaxy ends and the cluster begins. Yes, C1101 is famous because it appears to occupy this extreme category. It is not a spiral expanded to absurd size, with arms reaching across millions of light years. It is an enormous elliptical system, a vast old collection of stars whose shape reflects accumulation rather than delicate rotation. Its scale makes more sense when seen not as an isolated object, but as the product of a cluster environment. In a rich cluster, galaxies do not live quiet, independent lives. They move through a common gravitational field. They pass through hot gas. They are tugged, stripped, slowed, and sometimes merged. The central giant becomes a kind of archive of the whole cluster's past. Some of its stars may have formed in galaxies that no longer exist as separate systems. Some may have been pulled from the outskirts of passing galaxies and added to a diffuse envelope. Some may belong to populations so old that they formed when the universe was still young and crowded with smaller building blocks. This is why size is memory. A giant galaxy is not merely large because it contains many stars. It is large because it has gathered many histories into one gravitational body. The difference between a dwarf galaxy and a giant elliptical is therefore not only a difference of diameter or mass, it is a difference in the number of events carried within the system. A dwarf may preserve a simple and ancient record, a small flame that survived without being fully consumed. A spiral may preserve a balance between old structure and new birth, with stars still forming in cold gas along its arms. A giant elliptical may preserve the aftermath of repeated assembly, where the raw material for new stars is diminished, and the old stars drift in a broader, quieter swarm. Each type reveals a different way that matter can live inside the universe. Together, they show that galaxies are not just containers for stars. They are evolving environments, shaped by time, chance, and place. The largest galaxy ever found is meaningful only against this full range of forms. Without dwarf galaxies, the giant has no ancestry. Without spirals, it has no middle chapter. Without collisions, it has no path to grandeur. C1101 stands at the far end of this story, but it is not separate from the smaller systems that came before it. Its immensity is the accumulated result of ordinary galactic processes repeated on extraordinary scales. In its reddish light, the universe reveals one of its quietest truths. The largest structures are often built from countless smaller ones, gathered slowly until the original pieces can no longer be seen. IC 1101 enters the story of astronomy as a candidate titan, a galaxy so large in reported extent that it seems to test the meaning of a galaxy itself. It is often described as the largest galaxy ever found, a phrase that carries a certain grandeur, but also a quiet complication. In science, record holders are rarely simple. The tallest mountain depends on whether height is measured from sea level or from base to summit. The largest river depends on whether length, water flow, or drainage basin matters most. In the same way, the largest galaxy depends on what is being measured, how faint the outer light can be traced, and where the galaxy's own stars give way to the wider glow of the cluster around it. IK 1101 is real, immense, and exceptional. Yet its most famous measurements belong to the difficult edge of observation, where light becomes faint, boundaries blur, and the universe resists tidy categories. This does not make the galaxy less astonishing. It makes it more interesting. A simple record would be only a number. IC 1101 is a question about how far a galaxy can grow before its outskirts become almost indistinguishable from the environment that made it. When astronomers look at a galaxy, they are not seeing a solid object with a surface. They are receiving light from countless stars, some concentrated near the center, others spread thinly outward into an extended halo. The central regions are bright and easier to define. The outer regions are dimmer, more fragile in appearance, and more easily affected by the methods used to subtract background light, remove the glow of nearby objects, and interpret what remains. A normal spiral galaxy already has uncertain edges, because its stellar disk fades gradually, and its halo reaches farther still. A giant elliptical at the center of a cluster is even harder to contain with a clean line. It may be surrounded by a vast envelope of stars, some bound to the central galaxy, some torn from other galaxies, and some forming part of the diffuse light of the cluster itself. In this kind of environment, the phrase across can carry several meanings. It might refer to the bright central body. It might refer to a faint outer halo. It might refer to an even broader stellar envelope connected to the cluster. IC 1101 became famous because estimates of its full visible extent reach around 6 million light-years, a scale so large that it would stretch far beyond the distances between major galaxies in the local group. But such a number should be heard not as a hard edge, like the rim of a wheel, but as a measurement of extremely faint light spread through deep space. It is a way of saying that the system's influence and stellar envelope are enormous, not that a sharp wall of stars suddenly ends at that distance. The same caution applies to its mass and star count. ISKI 1101 is often associated with a possible total of up to 100 trillion stars, and with a mass far beyond that of the Milky Way. These estimates are not made by counting every star, because such a task would be impossible from Earth. Instead, astronomers infer stellar populations from light, color, mass-to-light ratios, and models of old stars. They estimate total mass by considering gravity, motion, cluster environment, and the presence of dark matter. The visible stars are only part of the story. Much of the mass that shapes a galaxy's behavior is unseen, belonging to the dark matter halo that surrounds and penetrates the luminous system. This dark matter does not shine, and it does not reveal itself through ordinary starlight, yet it is essential to the architecture of galaxies. Without it, the outer motions of stars and gas in many galaxies would not make sense. In a central cluster galaxy, dark matter is even more difficult to separate cleanly, because the dark matter halo of the galaxy overlaps with the larger dark matter distribution of the cluster. IC 1101 therefore occupies a grey zone between galaxy and cluster centre. It is a galaxy, but it is also embedded in a larger gravitational structure that has helped build it and may partly merge with its identity. Its scale is not just the scale of a solitary island. It is the scale of an island at the heart of an archipelago, surrounded by tides, debris, and the remains of long-ago collisions. The title of largest known galaxy is powerful because it compresses this complexity into a single image. It lets the mind picture one enormous object, wider than any familiar galactic form, containing more stars than ordinary intuition can hold. Yet a calmer and more accurate view is even more expansive. IC 1101 is not just a huge ball of stars floating alone in the dark. It is the brightest central member of a rich galaxy cluster, a system that likely became enormous by growing through repeated mergers and by gathering material from its surroundings. Its present form is a record of cosmic hierarchy, the way small things merge into larger things, and larger things sink into common centres. In such a setting, the largest galaxy is not an exception to the rules of the universe. It is the rules of the universe carried to an extreme. Gravity does not stop at a preferred scale. It continues to gather, sort, stretch, and combine matter wherever time and environment allow. A dwarf galaxy may fall into a spiral may merge with another spiral, a group may become part of a cluster, a central galaxy may absorb companions until its outskirts grow faint and vast. IC 1101 is remarkable because so many of these processes appear to have converged in one place. It is a record under shadow because the record is partly hidden by uncertainty, not because the object is doubtful, but because its greatness lies in a region where measurement is hard, its outer light is faint, its stellar halo is diffuse, its dark matter is invisible. Its central black hole cannot be weighed with complete confidence from simple observation. Even its exact rank among the largest galaxies can change depending on the criteria used and the discoveries still to come. Other enormous central galaxies exist in distant clusters, and some may rival it in mass, extent, or influence. Future surveys may refine its size downward, upward, or sideways, replacing the simple question of largest with a more careful set of categories. Largest by visible diameter, largest by stellar mass, largest by dark matter halo, largest by diffuse envelope, largest among galaxies whose outer light can be traced with a certain method. Science often turns one dramatic question into several quieter and more precise ones. This is not a loss of wonder. It is how wonder becomes durable. IC 1101 remains majestic when treated carefully. In fact, the caution deepens its mystery, because it reveals how hard it is to define the edge of anything so old and so massive. The galaxy's body has likely been built by the loss of many former boundaries, galaxies that once had their own centres, disks, arms, and halos may have been pulled apart and incorporated into the wider glow. Stars that once belonged to separate systems now move inside a common gravitational field. The more a galaxy grows by merging, the more its identity becomes collective. At some point, the question of where it ends is also a question of how many past galaxies are still being counted within it. Its famous size is therefore not only a measurement of space, but a measurement of accumulated history. The galaxy is huge because time has made it huge. It is smooth because violence has been repeated until the visible scars have softened. It is red because the bright young blue stars that once marked active birth have largely vanished from the main body, leaving older populations to dominate the light. It sits at the centre because gravity has carried mass inward through the cluster over immense spans of time. Each of these facts makes the title of largest less like a trophy and more like a clue. IC 1101 shows what can happen when a galaxy lives in the right environment for growth, with enough neighbours to consume, enough time to merge, and enough gravity to hold a vast envelope of stars. It also shows why the universe cannot always be divided into clean separate objects. The greatest things are often blended at their edges. A galaxy becomes a halo becomes cluster light. A central object becomes the visible heart of something larger and darker, from Earth, after its light has crossed about 1 billion years of expanding space. IC 1101 appears as a distant glow, far too remote for human senses to grasp directly. Yet within that glow is a structure large enough to make the Milky Way seem local, young, and modest. Its fame rests on numbers that should be handled gently, but even gentle numbers can be overwhelming. Whether it is the largest galaxy in an absolute sense, or one of the largest known examples of a central elliptical galaxy, it remains a cosmic extreme. It is a reminder that the universe does not need sharp edges to build something immense. It only needs gravity, darkness, time, and the patient surrender of smaller things into a greater whole. The light from IC 1101 begins its journey in a region of space so distant that its present appearance on Earth is already an ancient message. It lies roughly 1 billion light-years away, meaning the photons now arriving at telescopes left that galaxy when life on Earth was still moving through a far earlier chapter of its own history. The planet had no cities, no instruments, no eyes capable of turning upward with questions about distant galaxies. Yet while continents shifted, seas changed, and life continued its slow transformation, that light crossed the expanding universe, carrying with it the faint signature of a galaxy cluster called Albal 2029. This cluster is not a casual grouping of galaxies. It is a deep gravitational well, a vast association of galaxies, hot gas, and dark matter gathered into one enormous system. Near its centre sits IC 1101, bright, massive, and dominant, like the settled core of an old cosmic metropolis. To understand why such a galaxy can exist, the cluster matters as much as the galaxy itself. A central giant is not simply an oversized version of an ordinary galaxy placed in a random patch of space. It is the result of a special environment, one where many galaxies have spent billions of years moving through the same gravitational field, passing one another, disturbing one another, and gradually surrendering material to the region of greatest mass. In a cluster, space is not empty between galaxies in the simple everyday sense. It contains thin, extremely hot gas spread across enormous distances, glowing in high-energy light because it has been heated by the motions and collisions of the cluster itself. It also contains a great halo of dark matter, unseen but gravitationally decisive, shaping the orbits of the galaxies and holding the cluster together. The visible galaxies are only the jeweled points inside a broader architecture. They move through that architecture like slow sparks in a dark sea, each carrying its own stars, its own black hole, its own history of formation and loss. Over long stretches of time, interactions within the cluster can change them. A galaxy passing through the hot cluster gas may lose part of its own gas, the material it would otherwise use to form new stars. A smaller galaxy passing near a larger one may have stars stripped from its outskirts. Two galaxies that move slowly enough through the central region may merge, their separate forms dissolving into a larger common body. In the crowded core of a cluster, gravity has many chances to work. It tugs on halos, bends orbits, scatters stars, and slowly builds the kind of object that could never grow so large in isolation. IC 1101 is best understood as the central outcome of this long clustering process. It is often described as the brightest galaxy in a BL 2029, which means that within the cluster's visible population, it outshines the others. But brightness here is not only a matter of radiance, it points to accumulated mass, enormous stellar populations, and a position near the bottom of the cluster's gravitational well. In many rich clusters, the largest galaxy is found near the center, because the center is where mass gathers and where repeated interactions have the greatest opportunity to transform separate systems into one dominant elliptical. These central giants are sometimes surrounded by very extended halos of stars, so faint and diffuse that they blur into what astronomers call intracluster light, the light of stars no longer clearly bound to any one ordinary galaxy. This is one reason IC 1101 feels less like a single object with a neat border, and more like the luminous heart of a larger region. It belongs to the cluster, and the cluster has helped create it. The distinction between galaxy and environment remains real, but at the edges it becomes subtle. Stars stripped from smaller galaxies may drift through the cluster. Some may eventually become part of the giant galaxy's outer envelope. Others may remain in a diffuse population that traces the cluster's history rather than one galaxy's history alone. Around the central object, the past is spread thinly through space. Abel 2029 therefore acts as a setting, a mechanism, and a memory. As a setting, it places IC 1101 in a dense region where galaxies are not lonely. As a mechanism, it provides the gravity, neighbors, and repeated encounters that allow a central galaxy to grow. As a memory, it preserves the evidence of long cosmic assembly in its hot gas, dark matter, and extended light. The cluster is a place where the universe has concentrated matter on a scale far beyond the bounds of a single spiral. It is also a place where time has worn down distinctions. Galaxies that once moved independently may now be only partial contributors to the central glow. Gas that once belonged to star-forming disks may have been heated and dispersed into the cluster medium. Stars that once shone in smaller galaxies may now orbit within EC 1101, their origins hidden unless their chemistry or motion can be traced. In such an environment, growth is not gentle in the human sense, but it is slow enough to appear serene from a distance. The collisions of galaxies do not usually involve stars crashing into stars, because the spaces between stars are too large. Instead, the violence is gravitational. Orbits are rearranged, gas clouds are compressed or removed, black holes drift inward, stellar disks are stretched into tails, shells, and faint streams. Over time, the visible disorder can fade, leaving behind a smoother, larger elliptical form. From far away, the result may look calm, but its calmness is the aftermath of countless ancient disturbances. IC 1101's location near the center of Abel 2029 is therefore not incidental. It is the likely reason the galaxy reached such extraordinary scale. A central cluster galaxy has access to a long supply of potential mergers. It can grow by absorbing smaller galaxies, by merging with other large galaxies, and by accumulating stars stripped loose by the cluster's gravitational tides. The process is not rapid by ordinary imagination. It unfolds over hundreds of millions and billions of years. But the universe is old enough for slow processes to become powerful. A slight advantage in position, mass, or environment can compound across cosmic time until one galaxy becomes overwhelmingly dominant. This is the quiet arithmetic of structure formation. Matter falls toward denser regions. Dense regions become denser. The central object receives more opportunities for growth. In time, a galaxy like IC 1101 can emerge. Not because it broke the rules of galactic evolution, but because it lived inside a place where those rules were allowed to run for an immense duration. Its distance from Earth adds another layer of strangeness. The galaxy is not only far away in space, but also far away in time. The image observed now is an image from the past. Whatever changes have occurred in Abel 2029 during the last billion years remain unseen from Earth. The central galaxy may have continued to evolve. Smaller galaxies may have fallen inward. Gas may have cooled or heated in new patterns. The central black hole may have passed through quieter or more active phases. Human astronomy sees the cluster as it was when its light began the crossing, not as it is at this moment in cosmic time. This is true for all distant astronomy, but the effect becomes especially meaningful with a structure as large and old as IC 1101. The galaxy already appears ancient in the light that reaches Earth. Yet even that ancient appearance is delayed. It is an old object seen through an old message. The cluster around it is likewise a fossil image, a frozen arrival from deep time. Still, that light is enough to reveal the main truth IC 1101 is not a lone monarch, but the brightest central expression of a vast gravitational kingdom. Its throne is the core of Abel 2029. Its wealth is the accumulated light of stars formed in many places. Its size is tied to the invisible dark matter and cluster environment that surround it. The galaxy's grandeur cannot be separated from the web that holds it. In the wider universe, such central cluster galaxies show how structure grows from the bottom upward and from the outside inward at the same time. Small systems form early. Larger systems assemble from them. Clusters gather galaxies together. The central regions of clusters then build the most massive galaxies by collecting what time and gravity deliver. IC 1101 stands at this convergence point, where individual galactic history and cluster history become almost inseparable. It is a reminder that the largest galaxies are not merely objects of great diameter. They are places where the universe has concentrated memory, mass, and motion into one luminous center, shining from 1 billion light-years away with the soft authority of something assembled across nearly the whole age of stars. The most famous number attached to IC 1101 is its extraordinary reported span of about 6 million light-years, a measurement so large that it almost refuses to behave like a normal astronomical fact. A light-year is the distance light travels in 1 year, and light is the fastest messenger in nature. Even so, the bright disk of the Milky Way would take light more than 100,000 years to cross. The space between the Milky Way and Andromeda is only a few million light-years. A galaxy described as reaching 6 million light-years across is therefore not merely larger than a familiar spiral. It seems to occupy a scale usually reserved for the distances between major galaxies. Yet this number must be approached with care, because the edge of a galaxy is not like the shoreline of an island. It is more like a mist thinning into darkness, with stars becoming fewer, fainter, and harder to distinguish from the background of the wider cluster. A planet ends at a surface. A star fades through layers of gas until its visible photosphere gives astronomers a useful boundary. A galaxy has no such simple outer skin. Its central regions may blaze with concentrated starlight, but its outskirts dissolve gradually into a halo of scattered stars, globular clusters, faint streams, and dark matter that cannot be seen directly at all. For ordinary galaxies, this gradual fading already makes size a subtle question. For a giant central elliptical like IC 1101, the question becomes much more difficult, because the galaxy is immersed in the larger environment of Abel 2029. Around it may be a diffuse stellar envelope, and beyond that an even broader field of intracluster light, made of stars stripped from other galaxies and set adrift through the cluster's gravitational sea. When telescopes measure the faint outer glow, they are not simply drawing a clean border around one object. They are trying to understand which light belongs to the central galaxy, which belongs to the cluster, and which belongs to the long aftermath of galaxies torn apart in earlier encounters. The reported scale of IC 1101 therefore sits in the delicate space between observation and definition. It is not a false number, but neither is it a wall. It is a way of describing the reach of an immense stellar system whose outer light extends far beyond the compact form most people imagine when they hear the word galaxy. The deeper astronomers look, the more galaxies reveal extended outskirts. A spiral galaxy can have a bright disk, but it also has a faint halo populated by old stars and clusters. An elliptical galaxy can have a luminous body, but its light can continue outward in a smooth gradient until it becomes extremely hard to separate from the darkness around it. The choice of where to stop measuring depends on the sensitivity of the observation and the method used to define brightness. One study might measure a galaxy to the point where its light falls below a chosen threshold. Another might use models to estimate how far the stellar distribution continues. Another might consider gravitational influence rather than visible light. These are necessary tools for studying objects that do not announce their boundaries in simple ways. IC 1101 is so large and so embedded in cluster light that its diameter can change in meaning depending on which tool is being used. If only the brighter central body is counted, it becomes smaller, though still enormous. If the faint outer envelope is included, its reach grows. If the wider cluster environment is blended into the measurement, the scale becomes more majestic but also more ambiguous. This is why the phrase 6 million light-years across should be heard as a guide to grandeur rather than as a sharp ruler laid from one edge to another. It tells of a vast luminous domain, not a crisp circle. The same difficulty appears when comparing EC 1101 with the Milky Way. The Milky Way's bright stellar disk has one commonly cited size, but its halo extends much farther, and its dark matter halo farther still. If only bright starlight is counted, one number is used. If the halo is counted, another appears. If gravitational influence is considered, the boundary becomes entangled with the local group itself, because the Milky Way and Andromeda are falling toward one another within a shared environment. In this way, even home is hard to measure precisely. IC 1101 magnifies that problem to an extreme. Its outer parts may be shaped by the repeated absorption of smaller galaxies, by the stripping of stars from cluster members, and by the slow settling of material toward the centre of Abell 2029. Every faint star in its outskirts carries a possible history. Some may have formed in the main body long ago. Some may have arrived inside a smaller galaxy that was swallowed. Some may once have belonged to another cluster member before tidal forces removed them. By the time those stars are spread thinly across millions of light years, their membership becomes a question of motion, origin, and gravity rather than simple position. The edge of IC 1101 is therefore not only an astronomical boundary, it is a historical boundary. It asks when a stolen star becomes part of the thief, when debris becomes halo, and when the memory of a separate galaxy disappears into the central glow. To picture the scale, begin with familiar galactic distances and then let them grow wider. The Milky Way is a broad spiral home, with the Sun located far from the centre in one of its quieter regions, Andromeda. The nearest large spiral lies much farther away, yet still close enough in cosmic terms to be falling toward the Milky Way. A structure several million light-years across would reach across distances that can hold multiple major galaxies. If IC 1101 were placed in the local group in the broadest version of its reported extent, its envelope would not feel like a single galaxy in the ordinary imagination. It would feel like a sky-spanning region, overwhelming the scale of the neighbourhood. This comparison is dramatic, but it should remain gentle, because placing one galaxy into another environment is only a thought experiment. IC 1101 didn't grow in the local group. It grew in a rich cluster, where the density of galaxies and the depth of the gravitational well allowed a very different history. A galaxy that large is not simply a bigger copy of the Milky Way. It is an old central accumulation with a body shaped by mergers and a halo shaped by cluster tides. Its great diameter reflects not spiral arms extended outward, but a diffuse elliptical structure whose stars move in many directions, no longer organized into a flat rotating disk. In such a galaxy, scale is quiet rather than sharply drawn. There may be no grand blue arms, no delicate spiral lanes, no strong visual boundary. Instead, there is a swelling concentration of older light, strongest at the center, fading outward through an enormous, thin, almost ghostly envelope. The idea of 6 million light-years across becomes more haunting when understood this way. It is not the width of a bright wheel of stars. It is the reach of a stellar atmosphere built from the remains of long, cosmic accumulation. It is the distance over which an old galaxy's influence and history can be traced in light. At the outskirts, the stars may be so sparse that the darkness between them dominates. A traveller passing through such a region would not necessarily feel surrounded by brilliance. The galaxy would be present as gravity, as distant concentrations of light, as a membership in an enormous system, rather than as a glowing wall. From far away, telescopes gather the combined faintness into an image, but inside the outer halo the vastness would be almost empty. This is one of the strange truths of cosmic scale. The larger structures are not always dense. They are often large because they are spread out. A galaxy can be immense while much of its volume remains dark, thin, and silent. In IC 1101, the center may be crowded and brilliant, while the outer regions fade into a sparse frontier where individual stars are separated by tremendous distances. The number attached to the galaxy's diameter therefore describes both presence and absence. It describes the breadth of a system, but also the delicacy of its outer light. It describes a giant, but a giant made mostly of space. This is why measuring it requires patience and humility. Astronomers must subtract foreground stars, background galaxies, instrumental noise, and the glow of surrounding cluster material. They must decide how to model the fading profile of starlight. They must acknowledge that the result may be revised as better observations arrive. The cosmos does not always build objects with clean edges. It builds systems whose boundaries are written in gradients, histories, and gravitational relationships. EC 1101 is a sormus, not because it has a visible rim 6 million light-years from side to side, but because its light, mass, and ancestry extend through a region so wide that the very act of defining the galaxy becomes part of the mystery. The question is not simply how large it is. The quieter question is where a galaxy ends when it has spent billions of years becoming the center of everything around it. 100 trillion stars is not a number the mind can hold in any ordinary way. It is not like a crowd, a city, or even a sky full of points. It is a population so vast that comparison begins to collapse under its own weight. The Milky Way already contains hundreds of billions of stars, enough suns to make every familiar scale feel small, and yet IC 1101 is often described with a possible stellar count reaching into the tens of trillions, or even near 100 trillion. This estimate should be treated with the same calm caution that surrounds its diameter, because no telescope counts the stars one by one across such a distant and diffuse system. The number is inferred from light, from models of old stellar populations, from the galaxy's brightness, colour, and mass, and from assumptions about how many dim stars accompany the brighter ones that dominate what telescopes can see. Still, even as an estimate, the figure is powerful. It suggests a galaxy whose glow is not produced by a simple concentration of stars, but by an almost incomprehensible accumulation of stellar lives, gathered into one immense elliptical body over billions of years. Each star inside that count has its own physical story. Some are small red dwarfs, faint and long-lived, burning slowly enough to outlast most other kinds of stars. Some are aging giants, swollen and cool, shining with the reddish light that helps give old elliptical galaxies their warm colour. Some are white dwarfs, the dense remnants of stars that have already passed through their luminous final stages. Neutron stars and stellar black holes may also drift there, the compact remains of massive suns that died long ago. A galaxy as old as IC 1101 contains a long record of stellar generations, but not necessarily a rich supply of young blue stars. Its star count may be enormous, yet its ability to make many new stars appears greatly reduced. In this way, abundance and decline exist together. The light it sends across space is the light of an aging population, not the bright restless flame of a young spiral arm. Estimating the stars in such a system begins with luminosity, the total amount of light the galaxy emits. But light is not mass, and stars do not all shine equally. A single massive blue star can outshine many smaller stars while living only a brief time. A small red dwarf contributes very little light, but can add quietly to the total mass. Old galaxies are especially challenging because much of their stellar population may be faint. Astronomers therefore use mass to light ratios, which describe how much mass is likely present for a given amount of light. In an old elliptical, the absence of many young hot stars changes the calculation. The galaxy may contain vast numbers of dim, low-mass stars and stellar remnants that do not announce themselves strongly in visible light. The estimate of 100 trillion stars is therefore not a simple census. It is a model of hidden abundance built from the light that survives the journey to Earth. Around that stellar population lies an even larger mystery, dark matter. The stars of IC 1101, no matter how numerous, are only part of the galaxy's gravitational story. Across the universe, galaxies behave as though they contain far more mass than their visible stars and gas can explain. Stars in outer regions move in ways that imply the presence of additional matter that does not glow, absorb, or scatter light in ordinary ways. This unseen component is called dark matter, not because it is known to be black or shadowy in a familiar sense, but because it is invisible to telescopes except through gravity. It provides a hidden framework within which galaxies form and move. In smaller galaxies, dark matter can dominate the mass. In spirals, it helps explain why outer stars orbit faster than they would if only visible matter were present. IC 1101 sits inside this larger cluster setting, which makes the dark matter question especially subtle. The galaxy has its own stellar body, and likely its own dark matter halo. But it also lies at the centre of Abell 2029, where the cluster's dark matter halo is vast. The two may overlap so deeply that separating the mass of the galaxy from the mass of the cluster becomes difficult. The visible stars are like lamps inside a much larger invisible architecture. They reveal where matter has gathered, but they do not show the full structure that holds the system together. 100 trillion stars, if that estimate is close, would already represent a staggering visible mass. Yet the total gravitational mass associated with the central region may be far larger because of dark matter and hot cluster gas. The galaxy's greatness is therefore not only in its starlight, it is in the unseen gravitational field that allows such a body to exist at all. Without dark matter, the early universe would have had difficulty forming galaxies in the way observed today. Ordinary matter interacts with radiation and pressure. It resists collapse until conditions allow it to cool and settle. Dark matter, by contrast, can begin gathering through gravity without shining, forming invisible halos that help pull ordinary matter inward. Gas falls into these halos, cools, forms stars, and builds galaxies. In this view, the visible galaxy is the luminous result of an earlier invisible scaffolding. IC 1101, in its enormous maturity, is one of the grand expressions of that process. Its stars are the bright surface of a deeper gravitational history. The dark matter halo of its cluster may have guided the mergers that built it, drawing galaxies toward the center and helping create the conditions for repeated absorption. Yet over cosmic time, gravity is enough to create form from slight unevenness. A small excess of density grows, a halo deepens, gas falls inward, stars form, galaxies merge. A central giant accumulates. The result, after billions of years, can be an object whose visible population may reach numbers that once would have seemed mythic. The thought of 100 trillion stars also invites speculation about planets. Many are likely accompanied by planetary systems, though the environments around old elliptical galaxies may differ from those in younger spirals. The galaxy's older stars may host old planets, worlds that formed long before the Sun and Earth. Some may have been stable for immense stretches of time. Others may have been disturbed by close stellar passages in denser regions, by radiation from past activity, or by the gravitational consequences of mergers. The high star count increases the raw number of possible planetary systems, but it does not guarantee hospitable conditions. In science, more chances do not erase environmental limits. The inner regions of a giant elliptical may be crowded and bright. Some areas may have seen energetic activity from the central black hole. The galaxy may contain less cold gas and dust, meaning fewer new generations of stars and planets are being born today. Yet across such a vast system, diversity is almost unavoidable. No known evidence shows life in IC 1101, and no observation can yet examine its individual worlds. Still, the scale allows a careful kind of wonder. If the galaxy truly holds tens of trillions of stars, then even rare possibilities become numerous in principle. The calm mystery is not that life must be there, but that the number of settings is too large for intuition to comfortably judge. More important than speculation is the way the star count reveals the galaxy's past. 100 trillion stars cannot be formed easily in one quiet event. Such a population suggests generations of formation and assembly. Some stars likely formed in early galaxies that later merged into the central system. Others may have formed during bursts triggered by collisions. Many may have been born in separate galaxies that were eventually absorbed. The present star count is therefore a sum of many histories. It is not one family but many families mixed beyond recognition. The galaxy's light is collective, a softened blend from stars whose origins may have been spread across a wide region of the young universe. Dark matter gathered the stage, gas made the first stars, mergers rearranged the cast, time aged the light into red and gold. IC 1101 now appears as one vast object, but inside its glow are the remnants of countless smaller beginnings. Its magnitude is not merely numerical, it is historical, gravitational, and hidden. The stars provide the visible splendor, while dark matter supplies much of the silent depth. Together they make the galaxy less like a simple island of light, and more like a vast old continent, luminous on the surface, invisible in its foundations, and still difficult to measure even after its light has crossed 1 billion years to reach Earth. To understand the scale of IC 1101, the mind often has to return home first. The Milky Way is already enormous enough to overwhelm ordinary thought. It is a barred spiral galaxy with a bright disk wider than 100,000 light-years, a central bulge, graceful arms, a broad halo, and hundreds of billions of stars bound together by gravity. The Sun is not near its center, but far out in the disk, moving with countless other stars around the galactic core, from Earth. The Milky Way appears not as a full spiral, but as a pale river of unresolved starlight across the night. Because the solar system sits inside it, it is the surrounding city, not a distant object seen from outside. Every visible star in the night sky belongs to it, except for a few faint smudges that are nearby galaxies. The scale of home is therefore hidden by closeness. The galaxy feels like a backdrop, but it is a structure so large that light itself needs more than 100,000 years to cross its bright disk. Its spiral arms contain clouds of gas and dust where new stars continue to form. Its centre holds a supermassive black hole, quiet compared with the violent engines of active galaxies, but still massive enough to shape the inner region. Its halo contains old stars, globular clusters, and the remains of smaller galaxies that have been absorbed over time. Nothing about the Milky Way is small in human terms. It is only small when placed beside the greatest galaxies known. C1101 makes the Milky Way seem not insignificant, but local, delicate, and youthful by comparison. If its widest reported diameter is used, C1101 would span a region many dozens of times broader than the bright disk of the Milky Way. Its possible stellar population may exceed that of the Milky Way by hundreds of times, depending on the estimate used. But the comparison is not simply one of bigger and smaller. The two galaxies represent different evolutionary states. The Milky Way is still a structured spiral with gas, dust, and ongoing star formation. C1101 is a giant elliptical, smoother, older, and far more diffuse in its outer regions. The Milky Way is still building parts of itself. C1101 looks more like the product of long assembly after many earlier chapters have ended. The contrast becomes sharper when Andromeda is added to the picture. Andromeda is the nearest large spiral galaxy to the Milky Way, a vast system lying about 2.5 million light-years away. It is larger and more massive in some respects, with a broad disk, a bright central region, and a surrounding population of satellite galaxies. Like the Milky Way, it is not alone. Both galaxies belong to the Local Group, a modest galactic neighbourhood containing several dozen known members, many of them dwarfs. The Milky Way and Andromeda dominate this group, while smaller companions such as the Magellanic Clouds, Triangulum, and numerous dwarf spheroidal systems move within their combined gravitational influence. In the distant future, the Milky Way and Andromeda are expected to merge, creating a larger elliptical or lenticular remnant sometimes imagined under the informal name Milkdromeda. This future merger will be immense by local standards. Spiral arms will be distorted. Gas may be compressed into new stars. The central black holes will eventually move toward a common center. Stars will be scattered into new orbits. The familiar form of the Milky Way will disappear. Yet even this future merged galaxy would likely remain modest compared with C1101. The Local Group itself, in terms of major galaxies, is not a rich cluster. It is a quieter region, large to its inhabitants but sparse compared with the dense environment of Abell 2029. This matters deeply. Because environment determines opportunity. The Milky Way and Andromeda have only a limited supply of large neighbours to merge with. C1101 grew in a cluster where many galaxies could contribute mass over time. Its scale is not just the outcome of internal growth, but of a crowded cosmic address. A thought experiment is often used to make the difference vivid. If C1101 were placed where the Milky Way now resides, its broad stellar envelope could reach far beyond the familiar bounds of the Local Group, depending on how its outer extent is defined. It could encompass regions associated with the Large Magellanic Cloud, the Small Magellanic Cloud, Andromeda, and Triangulum. not as a dense blazing object filling every point of space, but as a vast gravitational and stellar presence spread across distances that now separate major galaxies. This image can be misleading if taken too literally, because IC 1101 would not simply fit into the local group as a bright solid sphere. Its outer regions are faint and diffuse. Much of the volume inside such a diameter would still be nearly empty by everyday standards. But as a comparison of scale, it is powerful. The local group, which seems so grand from within, could be treated almost as a region inside the reach of one extreme central elliptical. What feels like an entire neighbourhood from the viewpoint of the Milky Way becomes a measure across the outskirts of a larger giant. The emotional effect of this comparison is not to diminish home, but to reveal how layered cosmic scale is. Earth is vast to a person. The solar system is vast to Earth. The Milky Way is vast to the solar system. The local group is vast to the Milky Way. A galaxy like IC 1101 can then appear vast even beside the local group. Beyond it, clusters, superclusters, and the cosmic web continue the pattern. Scale in astronomy is not a single leap into largeness. It is a staircase where each step becomes almost unimaginable, and yet another step remains above it. Still, comparison must preserve the physical differences between these systems. The Milky Way has a flattened rotating disk. Its stars generally orbit in an organized pattern around the center, though with many variations. Its arms are regions of active gas and star formation. Andromeda has a similar spiral identity, though with its own history of mergers and disturbances. IC 1101, by contrast, is not held in the same graceful disk. Its stars move in more varied orbits, giving the galaxy its broad elliptical shape. It has likely consumed many systems whose former disks and arms have been mixed into a smoother distribution. Its light is older. Its gas supply for star formation is lower. Its central environment is shaped by a cluster rather than by a small group. It is not the Milky Way enlarged. It is a different outcome of galactic evolution. The comparison therefore has two meanings at once. By size, IC 1101 makes the Milky Way seem like a minor structure. By character, it shows what repeated merging and aging can do to galaxies over cosmic time. The Milky Way is not destined to become EC 1101 because its environment is different. It will merge with Andromeda and perhaps with smaller companions. But it does not sit in the centre of a rich cluster with a deep supply of neighbouring galaxies. Its future remnant may become larger, redder, and smoother, but probably not a Titan of the same class. In this way, IC 1101 is not simply the Milky Way's future, it is a future that belongs to galaxies in more crowded and massive regions. Home will age, but not every aging galaxy becomes one of the greatest giants. Some become quiet remnants on smaller scales. Others remain spirals for long periods. Others are stripped, disrupted, or absorbed. Cosmic evolution has patterns, but not a single path. The beauty of comparing EC 1101 with the Milky Way is that it joins intimacy with distance. The Milky Way is the known reference, the galaxy that made the Sun, Earth, and the conditions from which life emerged. Andromeda is the neighbouring giant, close enough to shape the far future of that home. The local group is the wider family, a small association of galaxies bound together in shared gravity. IC 1101 stands far beyond that family, in a richer and older city of galaxies, showing what happens when the same forces operate with greater mass, more neighbours, and more time. It makes home small, but not meaningless. The Milky Way is small only in the same way a single star is small beside a galaxy, or a single world is small beside a star. Its smallness is relational, not empty. Within it, stars continue to form, planets continue to orbit, and ancient light continues to move through dust and darkness. I see 1101 widens the frame until the Milky Way becomes one example among many, a luminous spiral in a universe that can also produce colossal red ellipticals spanning scales that feel almost intergalactic. In that widened frame, the largest known galaxies do not erase the importance of smaller ones. They reveal the depth of the process that connects them, from dwarf companions to spiral homes, from future mergers to cluster giants, from a faint band across Earth's sky to a galaxy so immense that even a whole local neighborhood can seem like a small region beside it. Built by ancient collisions, I see 1101 is less a single birthplace than a long gathering of former galaxies. Its immense body is the visible result of a process that has shaped cosmic history from the beginning. Smaller systems fall together, disturb one another, merge, and leave behind something larger than either ancestor. This process is not rare. It is one of the ordinary engines of galactic evolution. The universe expands overall, carrying distant galaxy clusters away from one another. Yet within bound regions, gravity still wins locally. Galaxies in the same group or cluster can drift, fall, and collide over spans of time so long that the word collision almost becomes misleading. They do not usually strike like solid objects. Their stars are so widely separated that direct stellar impacts are uncommon. What collides most powerfully is gravity, along with gas, dust, dark matter halos, and orbital order. A galaxy approaching another galaxy feels a broad tidal pull. Its outer stars can be loosened, its gas clouds can be compressed, its disk can warp. Long tails of stars may be drawn outward, while the central regions begin a slow inward dance. Over hundreds of millions of years, the separate forms can pass through one another again and again, each encounter robbing the pair of some orbital energy until their cores finally settle into a common remnant. In a rich cluster, such events may repeat over and over, and each repetition adds another layer to the final galaxy. I see 1101 appears to be one of these final accumulations, a giant elliptical shaped not by a single dramatic event, but by a long sequence of mergers whose details are mostly lost in the smoothness of its present light. The earlier stages of its ancestry likely began when the universe was much younger, with smaller galaxies forming inside dark matter halos. These early galaxies were probably irregular, gas-rich, and crowded with star formation. Some may have been dwarfs, faint by the standards of later cosmic giants. Others may have grown into larger systems through their own mergers before becoming part of the central cluster history. As the region that would become Able 2029 gathered mass, galaxies within it were drawn into a shared gravitational environment. The densest regions attracted more matter. The central halo deepened. Gas was heated. Smaller galaxies moved through the cluster like embers in a great unseen wind. Those near the centre had the highest chance of being absorbed by the growing dominant galaxy. A large early elliptical may have formed first, then continued expanding through additional mergers, or several major galaxies may have combined in stages, creating a central object whose mass gave it an increasing advantage. Once a galaxy becomes the dominant body near a cluster centre, its growth can become self-reinforcing. It has a larger gravitational reach. It can disturb nearby companions more effectively. It can become the natural endpoint for galaxies whose orbits slowly decay toward the cluster core. This does not mean every nearby galaxy simply falls in. Many remain independent for immense periods. Some move too quickly to merge. Some are stripped but not swallowed. Yet across billions of years, the central giant receives enough contributions for its body to swell far beyond ordinary galactic scale. The evidence for such assembly is written into the nature of giant ellipticals. They are usually old, red, and smooth because the ordered disks of their ancestors have been scrambled. A spiral galaxy has a memory of rotation in its shape. Its arms and disk reveal a shared plane of motion. When spirals merge, that order is disturbed. Stars are thrown onto new orbits that point in many directions. Gas loses angular momentum, falls inward, ignites starbursts, or becomes heated and unavailable for later star formation. The result can be a galaxy with little disk structure, a broad elliptical swarm where the stars no longer trace graceful arms. Repeated mergers make the final form even smoother, as each new addition stirs the old structure into a wider distribution. IK 1101's lack of spiral arms is therefore not an absence of history. It is the consequence of too much history blended together. If it once absorbed spiral galaxies like the Milky Way or Andromeda, their arms did not survive as recognizable features. Their stars were scattered into the greater envelope. Their gas may have been consumed, stripped, or heated. Their black holes may have sunk toward the central region, influencing the core and perhaps merging with the central black hole over time. The original shapes faded, but their mass remained. This is how a galaxy can grow while losing visible complexity. The delicate forms disappear, and the object becomes larger, older, and more uniform. Galaxy mergers also help explain why giant ellipticals can be poor in cold gas. In a first encounter between gas-rich spirals, clouds of gas may be compressed, causing bursts of new star formation. For a time, the merger can shine with youthful blue stars and turbulent energy, but this activity consumes gas quickly. Feedback from massive stars, supernovae, and central black holes can heat or expel gas. In a cluster environment, hot intra-cluster gas and rapid motion can strip additional gas from galaxies before they ever merge. Over time, the central galaxy receives many stars but not always enough cold gas to continue forming new generations. It becomes rich in old light and poor in the raw material of renewal. IK 1101's yellow-red colour reflects this mature state. Its stars are numerous, but many are old. The galaxy has grown by accumulation more than by continuing birth. It is a monument to mergers that built mass while slowly exhausting the conditions for widespread star formation. The central black hole may also participate in this transformation. During mergers, gas can be driven toward galactic centers, feeding black holes and producing active phases in which enormous energy is released. Jets, radiation, and outflows can heat surrounding gas, making it harder for that gas to cool into new star-forming clouds. IC 1101's central engine is not directly known with perfect precision, but its expected scale is consistent with a galaxy that has grown through repeated mergers. Every swallowed galaxy may have brought its own central black hole. Over time, many of these could have spiraled inward, merged, or disturbed the core, contributing to the formation of a massive central darkness. The galaxy's visible body and hidden engine may therefore have grown together, linked by the same history of assembly. This connection is one reason giant galaxies and giant black holes often appear related. The relationship is not simple, but it reflects a shared past in which gas, stars, and black holes all respond to gravity over cosmic time. In IC 1101, the mergers are no longer seen as fresh tidal arms or bright blue starbursts. They are seen in the result as central giant with enormous reach, old stellar populations, and a likely massive black hole at its heart. The violence has cooled into structure. The former galaxies have become the present one. Even so, traces of the past may still survive in faint forms. Around giant ellipticals, astronomers sometimes find shells, streams, or subtle changes in the motion and chemistry of stars. These are the remaining fingerprints of swallowed galaxies. A star stream can mark the path of a disrupted companion. A shell can form when stars from a merger pile up at certain points in their orbits. Differences in chemical composition can reveal that not all stars were born in the same original system. For IC 1101, its distance makes many such details difficult to study, but the general principle remains. A smooth giant need not be simple. It may contain hidden layers like sediment in an ancient landscape, each layer corresponding to a different episode of growth. The present galaxy is the integrated light of all those episodes. Its size is what ordinary physics can produce when supplied with enough matter, enough neighbours, enough time, and a deep enough gravitational well. This makes IC 1101 both extreme and natural. It is extreme because few galaxies reach such reported dimensions. It is natural because the processes that built it are visible in smaller forms throughout the cosmos. The Milky Way continues to absorb dwarf companions. Andromeda shows signs of past mergers. Galaxy pairs across the universe display bridges, tails, and distorted arms. Clusters contain central giants surrounded by diffuse light. IC 1101 is part of this same story, only written in a larger script. Its ancient collisions are no longer roaring events but settled consequences. The galaxy drifts now as a broad red remnant, holding within it the stars of many lost systems. Each absorbed galaxy gave up its separate outline, but not its existence. Its stars still shine somewhere in the wider body. Its dark matter helped deepen the gravitational field. Its black hole and remnants may have contributed to the central structure. The final object is therefore not a destroyer alone, but a collector. It gathers, erases, preserves, and transforms. In the quiet light of IC 1101, the universe shows how creation and loss can be the same process viewed at different scales. Smaller galaxies vanish as separate forms, while a larger galaxy comes into being. The collision ends one history and extends another. Over billions of years, repetition turns this exchange into grandeur, until the central giant becomes a calm monument to everything it has consumed. The quiet red light of IC 1101 is one of the most important clues to its age and condition. A galaxy can appear blue, white, yellow, or red, not because the galaxy has a single surface colour like a painted object, but because its many stars combine their light into one broad signal. Young, massive stars burn hot and blue, but they live briefly, exhausting their fuel on timescales that are short by galactic standards. Older, lower mass stars live much longer and shine with softer yellow, orange, and red tones. When a galaxy is rich in cold gas and actively forming stars, new blue stars continually appear, refreshing its colour and marking regions of recent birth. When a galaxy has lost much of that cold gas, or when its gas has become too hot and thin to collapse easily, the bright blue population fades away. What remains is the longer-lived starlight of older stars. IC 1101 belongs to this quieter category. Its immense body is not known for spiral arms glowing with stellar nurseries, or for dark dust lanes full of future suns. It is an old elliptical system, broad, smooth, and reddish, shaped by mergers that made it larger, while also helping drain or heat the material needed for widespread renewal. Its colour is therefore not merely an aesthetic feature, it is a record of time. It says that the galaxy has passed through the most vigorous phases of starbirth and now shines mainly by the persistence of stars formed long ago. In a spiral galaxy, the cycle of star formation can remain visible across the disk. Cold molecular clouds gather in arms. Gravity compresses them. New stars ignite in clusters. Massive young stars flood the surrounding gas with ultraviolet light. Some explode after brief lives, returning heavy elements to space and stirring the next generation. The process is not constant everywhere, and it can rise or fall with local conditions. But the presence of gas allows the galaxy to remain generative. IC 1101 is different. It may still contain some gas, and small pockets of star formation may occur under special conditions. But the overall system is no longer a vibrant star factory. The vast majority of its light is thought to come from older stellar populations, the kinds of stars that survive after the hot blue ones have vanished. This is common among giant ellipticals, especially those at the centers of galaxy clusters. Their histories are full of mergers, and mergers can both trigger star formation and help end it. During an encounter, gas clouds may collide, fall inward, and form stars rapidly, but that rapid formation consumes gas. At the same time, energy from supernovae and central black hole activity can heat gas or push it outward. In a cluster environment, galaxies can also lose gas as they move through the hot intra-cluster medium, the thin searing plasma that fills the space between cluster members. The central giant may grow rich in stars while becoming poor in the cold raw material from which many new stars are made. The result is a strange kind of aging abundance, more stars than almost any ordinary galaxy, yet less capacity for youthful renewal. IC 1101's redness should not be imagined as weakness. It is not a dying ember in the sense of being small or faint. It remains enormous and luminous, with the accumulated glow of an immense stellar population. But its light is old light. It comes from stars that have settled into long lives, stars that do not burn with the intense blue brilliance of newly formed massive suns. Many of the most massive stars that ever formed in the galaxy's ancestors have already ended, leaving behind neutron stars, black holes, white dwarfs, and enriched gas. Smaller stars continue to shine quietly. Red giants expand near the ends of their lives. Ancient star clusters orbit in the halo. The galaxy's colour blends all of this into a warm, aged radiance. A telescope does not directly show the biography of each star, but the combined light speaks statistically. The colour, spectrum, and brightness reveal a population that has lived through much of cosmic time. This is why giant ellipticals often feel like fossils, though the word fossil must be used carefully. They're not dead objects frozen in place. Their stars still move, their black holes still exert gravity, their hot gas still shifts, cools, heats, and responds to energy. Their outer halos still interact with smaller galaxies and cluster tides, but they preserve the outcome of earlier eras more strongly than they display ongoing birth. They are active in gravity, but quiet in star formation. The slow reddening of a galaxy is tied to the lifespans of stars. Massive blue stars are bright because they burn fuel quickly. Once a starburst ends, these stars disappear from the galaxy's light relatively soon in cosmic terms. The surviving population becomes dominated by stars that live longer and shine cooler. Over time, the overall colour shifts. This process makes a galaxy's light into a clock, though not a simple one. Dust can redden light, metal content, meaning the abundance of elements heavier than hydrogen and helium, can affect colour and spectra. Different generations of stars can overlap. Still, for a giant elliptical like IC 1101, the red and yellow tones strongly suggest an old population with limited recent star formation. Metal richness adds another layer. Stars that formed after earlier generations had lived and died can contain more heavy elements, because supernovae and stellar winds enrich the gas from which later stars are born. A giant elliptical assembled from many galaxies may contain stars of many chemical backgrounds, some ancient and metal poor, others more enriched. The integrated light becomes a record not only of age, but of previous generations that forged heavier elements and returned them to space. In this way, the The quiet red galaxy is not simple or empty. It is chemically layered, dynamically complex, and historically deep. Its apparent stillness is the calm surface of a system that has already spent much of its fuel for new stars. The lack of cold gas in giant ellipticals is not always absolute. Some may acquire gas through minor mergers, stellar mass loss, or cooling from hot halos, but the gas often struggles to form stars efficiently. It may be heated by the central black hole, stirred by cluster motions, or spread too thinly to collapse. In a central cluster galaxy, the surrounding hot gas can in some cases cool toward the center, but energy from the central black hole may repeatedly reheat it, creating a feedback cycle. Such feedback can act like a thermostat on a cosmic scale. Gas begins to cool and flow inward. The black hole is fed. Energy is released through radiation, jets, or bubbles in the surrounding medium. The gas is heated again, and star formation is suppressed. This pattern is seen in many cluster centers, though the details vary from system to system. IC 1101 may belong to this broad family of galaxies where the central engine and cluster environment help keep the galaxy old, red, and quiet. Its immense size does not prevent decline in starbirth. In fact, its size and location may be part of the reason that decline became so complete. The more massive and central a galaxy becomes, the more strongly it can heat, disturb, or lose the gas that might otherwise renew it. There is a deep tenderness in this stage of galactic life. The galaxy is not ending quickly. It is fading on timescales far beyond human history, far beyond the age of civilizations, even far beyond the lifetime of many stars. New stars may still appear here and there, but not in numbers large enough to transform the whole system. The existing stars will age. Some will swell and shed their outer layers. Some will become white dwarfs. The smallest red dwarfs may keep burning for extraordinary spans of future time. The galaxy will not explode as a whole. It will not vanish in one event. It will simply become dimmer as its bright stars finish their lives and fewer young stars replace them. This is the slow death of a galaxy, not destruction, but the gradual exhaustion of luminous renewal. IC 1101 shows that even the greatest structures can enter such a twilight. Its sheer scale does not make it young. Its abundance does not make it fertile. It is a giant made of aging light, sustained by the long patience of smaller stars and stellar remnants. Its past was shaped by motion and merger, but its present appearance is one of vast restraint. The blue blaze of youth has mostly passed into memory. What remains is the broad glow of an old elliptical at the heart of a cluster, a galaxy that has gathered countless stars and yet now forms relatively few. In that reddish light, the universe offers a calm paradox. Growth can lead to quietness, collision can lead to smoothness, abundance can lead to exhaustion. IC 1101 is not only large because it has consumed many histories, it is red because those histories have aged together, their brightest flames gone, their long-lived stars still shining softly across a distance of about 1 billion light-years. At the centre of EC 1101, hidden beneath the glow of countless old stars, there is expected to be a dark engine of extraordinary scale. Nearly every large galaxy studied in enough detail appears to contain a supermassive black hole near its core, and the largest galaxies are often associated with the largest central black holes. The Milky Way has one, called Sagittarius A star, with a mass of millions of suns. Many giant ellipticals contain black holes measured in billions of solar masses. IC 1101, because of its size, its central position in a galaxy cluster, and the history of mergers that likely built it, is often imagined as the home of something even more extreme, an ultramassive black hole. The word ultramassive is not a separate kind of object in the way a planet is separate from a star. It is a way of describing a black hole so massive that it lies at the upper end of the known range, far beyond the central black holes of ordinary large galaxies. Such a black hole would not be a hole in space in the everyday sense, but a region where gravity has become so intense that inside a boundary called the event horizon, no light can escape. Outside that boundary, its influence reaches through the surrounding stars and gas, shaping motion, heating material, and sometimes powering jets or radiation if matter falls toward it. For IC 1101, the difficulty is that the black hole cannot be weighed as easily as the black hole in a nearby galaxy. The galaxy is about 1 billion light-years away, and its central region is crowded, luminous, and hard to resolve. Astronomers cannot simply look at the black hole directly. Even black holes in much nearer galaxies are inferred through their effects. Their masses are estimated by measuring the orbits of stars, the motion of gas, or the behavior of light coming from material near the center. For a distant giant elliptical, these measurements become far more uncertain. The core may appear bright and smooth, but the details needed to pin down the central mass are blurred by distance and by the combined light of many stars. As a result, the black hole in IC 1101 is often discussed through inference rather than direct measurement. Its possible mass has been speculated to be tens of billions of times the mass of the Sun, sometimes with upper estimates reaching even higher. But the uncertainty is large. This uncertainty matters. It is tempting to say that the largest galaxy must contain the largest black hole, yet nature does not always follow simple ranking. Galaxies and their central black holes are related, but not with perfect obedience. A very massive galaxy tends to host a very massive black hole, because both grow through some of the same processes. Gas flows inward, stars collect in the central regions, galaxies merge, bringing their black holes together. But the exact mass of any one central black hole depends on details of feeding, merger history, feedback, and the structure of the galaxy's core. Some black holes may grow rapidly during active phases, when gas falls in and releases tremendous energy. Others may remain underfed for long periods, massive but quiet. Some may merge with other black holes after galaxy collisions. Some may be kicked, displaced, or left in complex orbital histories before settling. IC 1101 likely carries such a complicated past. If it was built from many galaxies, then many central black holes may have been delivered toward its core across cosmic time. Some may have merged with the main black hole. Some may have influenced the central star distribution while spiraling inward. The result could be a huge dark mass at the center, but the exact total remains difficult to know. The core of a giant elliptical can preserve signs of this history. When two galaxies merge, their central black holes do not instantly combine. They first sink toward the common center through gravitational interactions with surrounding stars and gas. As they orbit each other, they can fling stars away from the central region, carving out a lower density core. Eventually, if conditions allow, the black holes move close enough to merge, releasing gravitational waves, ripples in space-time. Repeated mergers can enlarge the central black hole, while also reshaping the inner galaxy. For a galaxy as large as IC 1101, the central region may be the long-term aftermath of many such events. The darkness there is not simply a passive anchor. It may be one of the forces that help define the galaxy's present state. A massive black hole can regulate its surroundings through feedback. When gas falls toward it, the gas forms a hot, bright structure called an accretion disk, unless the flow is too thin or disrupted. Friction, magnetic fields, and extreme gravity heat the material until it can shine intensely. In some galaxies, narrow jets of energetic particles are launched from the central region, extending far into space. These jets do not come from inside the event horizon, because nothing escapes from there. They are produced by processes in the rotating material and magnetic fields outside it. When such energy enters the surrounding gas, it can prevent that gas from cooling. This is one way a giant elliptical can remain red and quiet. The galaxy may have enough hot gas nearby, but the central engine repeatedly stirs and heats it, making widespread star formation difficult. The black hole therefore participates in the slow aging of the galaxy. It does not consume every star around it, and it is not a cosmic vacuum cleaner pulling in the whole system. Most stars orbit safely at great distances, but the energy released by small amounts of infalling matter can affect gas across enormous scales. In this way, the black hole's influence is not measured only by what it swallows. It is measured by how it changes the future of star formation around it. In IC 1101, this possible feedback belongs to the larger story of a cluster center. The galaxy sits amid hot intra-cluster gas, and the interaction between that gas and the central black hole may help maintain the old elliptical state. If gas cools toward the center, the black hole may be fed. If the black hole is fed, it may release energy that heats the gas again. The cycle can repeat, keeping the galaxy from producing large numbers of new stars even though matter is present. This balance is subtle and imperfect, but it helps explain why some of the most massive galaxies are not the most active star-forming galaxies. They have grown huge, yet they have become quiet. Their central engines may be part of the reason. The idea of an ultra-massive black hole also raises a deeper question about limits. How large can a black hole become? Some theoretical discussions suggest that growth may become inefficient beyond extremely high masses, because the surrounding disk of material may become unstable, or because fuel is no longer easily delivered. Yet the universe has produced quasars with black holes weighing tens of billions of suns, even at great distances and early times. These objects show that black hole growth can be surprisingly rapid and extreme under the right conditions. IC 1101's central black hole, if it truly lies in that range, would belong among the most massive known or suspected black holes. But because its mass is not securely measured, it remains in the realm of careful possibility. It may be one of the greatest dark engines in the nearby observable universe, or it may be smaller than the most dramatic estimates. Either way, it is almost certainly immense by human standards. The uncertainty does not weaken the mystery. It protects it from false precision. Science is strongest when it allows the unknown to remain unknown until better evidence arrives. For now, the central darkness of EC 1101 is known mostly through expectation, indirect signs, and comparison with other giant ellipticals. The galaxy's scale suggests a correspondingly massive core. Its cluster environment suggests a history rich in mergers. Its quiet red condition suggests that central feedback may have played a role in suppressing star formation. These threads point toward an ultramassive black hole, but they do not fully reveal it. Somewhere in the heart of that distant giant, surrounded by old stars and the softened remnants of former galaxies, gravity likely gathers into a region from which no light returns. Around it, stars move in orbits shaped by a mass they cannot touch. Gas heats, cools, and perhaps falls inward in rare episodes. The galaxy's past converges there, and its future is quietly influenced by what the dark center does with the matter that reaches it. IC 1101 is famous for its size, but its center may be just as important as its outer halo. The largest visible body points inward to one of the deepest invisible questions: how much darkness can a galaxy carry at its heart, and how much of its long fading life is guided by that unseen anchor? The thought of life inside IC 1101 begins with a simple imbalance between knowledge and possibility. The galaxy may contain tens of trillions of stars, perhaps even a population often described as approaching 100 trillion. and many stars in the universe appear to be accompanied by planets. On numbers alone, such a galaxy seems to offer more chances than almost any other single galactic system known. Yet life is not produced by numbers alone. It depends on chemistry, stable environments, long-lived energy sources, planetary surfaces or oceans, shielding from destructive radiation, and enough time for complexity to arise without being erased. IC 1101 offers time in abundance, but its environment is not the same as the quiet spiral neighborhood where Earth formed. It is an old giant elliptical galaxy, likely built by many mergers, poor in the cold gas that makes new stars, and shaped by the history of a dense cluster center. Its stars are numerous, but many are ancient. Its central regions may be crowded. Its core may hold an ultramassive black hole whose past activity heated gas and helped shut down star formation. To ask whether life could exist there is therefore to hold two truths at once. The sheer number of stars widens the field of possibility almost beyond intuition, while the conditions inside the galaxy may make many of those chances less gentle than a first glance suggests. Life as known from Earth requires more than a star and a planet. It requires elements heavier than hydrogen and helium, such as carbon, oxygen, nitrogen, phosphorus, sulfur, iron, and others that participate in rocks, atmospheres, oceans, and living chemistry. These elements were not common in the earliest universe. They had to be made inside stars and spread by stellar winds and explosions. In this respect, an old giant elliptical may have an advantage. Many of its stars likely formed after earlier generations had already enriched gas with heavier elements. A metal-rich stellar population can support rocky planets more readily than one made from nearly primordial material. The warm colour of IC 1101 suggests old and often enriched stars. Although the details vary across the galaxy, some stars may be extremely ancient and poorer in heavy elements. Others may have formed in later or more enriched environments before their host galaxies merged into the giant. The galaxy is therefore not chemically uniform. It is a vast mixture of stellar histories. Somewhere within that mixture, rocky planets may well exist, around long-lived smaller stars. Such planets could remain in stable orbits for spans of time much longer than the age of the Sun. On this level, the galaxy seems rich with possibility, not because life is known there, but because the raw ingredients and the time may both be present in many places. The challenge is that old galaxies can also be quiet in the wrong way. When star formation slows, the birth of new planetary systems slows with it. IC 1101 may have formed many of its stars long ago, meaning many of its planets, if present, may also be ancient. Ancient worlds are not automatically lifeless. Some may remain geologically active for long periods if they are large enough, warmed by tidal forces, or insulated beneath ice. Others may have cooled, lost atmospheres, or passed through long climate changes. Around smaller red stars, planets could receive steady light for extraordinary durations, but such stars may also flare strongly, especially in youth, stripping atmospheres from close worlds unless magnetic fields or atmospheric replenishment protect them. Around aging stars, habitable zones move outward as stars brighten, leaving inner planets overheated and outer planets perhaps briefly warmed. In a galaxy dominated by older stellar populations, many planetary systems may have already moved through major transitions. Some could be barren remnants, some could be frozen, some could orbit dead stellar cores, some could remain stable and temperate around long-lived stars, carrying oceans through ages far longer than Earth has existed. The possibility is not a single answer. It is a spectrum spread across trillions of systems that cannot yet be observed directly. The cluster environment adds another difficulty. IC 1101 sits at the centre of Abel 2029, where galaxies, hot gas, dark matter, and old gravitational scars surround one another. In such a region, the galaxy may have experienced intense episodes in its past. Mergers can disturb stellar orbits. They can drive gas toward the centre, feeding black hole activity. They can trigger bursts of radiation and star formation, followed by heating and exhaustion. Near the central regions, stellar density may be high, raising the chance of closer stellar encounters over long periods. Such encounters can perturb planetary orbits, disturb distant comet reservoirs, or alter the stability of fragile systems. The danger would not be evenly distributed. The outskirts of a giant elliptical may be much more sparse, with stars separated by broad distances, perhaps offering quieter locations. The inner regions may be bright, crowded, and more exposed to energetic events. The galaxy is too large for a single description of habitability to apply everywhere. It may contain regions that are hostile, regions that are merely old, and perhaps regions that are stable enough for complex chemistry to endure. Radiation is another part of the balance. A massive central black hole is not dangerous across an entire galaxy simply because it exists. Most stars can orbit far from it without being swallowed or directly threatened. But during active phases, when gas falls inward and energy is released, the central engine can affect surrounding gas and perhaps bathe inner regions in stronger radiation. Supernovae also matter, especially in periods of intense star formation. In the present old elliptical state, massive young stars are less common, so the rate of certain violent stellar deaths may be lower than in a blue star-forming galaxy. That could make some regions calmer now than they were during earlier merger-driven episodes. Yet the past still matters for life. If planets formed early and then endured phases of higher radiation, their atmospheres and surfaces may have been altered. Some environments, especially subsurface oceans or worlds shielded by ice, rock, or thick atmospheres, might withstand such conditions better than exposed land worlds. The search for life in any galaxy must therefore look beyond Earth-like surfaces alone. Moons, ocean worlds, deep crustal habitats, and planets beneath dense atmospheres could provide hidden refuges in EC 1101 if life exists. Some of it might be buried away from the bright and restless history of the galaxy, sustained by chemistry and internal heat rather than open skies. The age of the galaxy invites another speculation. Could intelligence have had more time to arise there than in the Milky Way? Some stars in EC 1101 may be billions of years older than the Sun. If their planets remained stable, biological evolution could have had immense durations to unfold. But more time does not guarantee more complexity. A planet can remain simple for long ages, or suffer repeated resets, or never develop the right conditions at all. Intelligent life may require not only stability, but also contingency, a rare sequence of events in geology, atmosphere, oceans, climate, chemistry, and extinction. A giant galaxy with countless old planets increases the number of possible attempts, yet it also includes many systems that may have aged past their most favourable eras. Civilizations, if they ever emerged, would face the same grand indifference as any life elsewhere, because stars change, planets shift, resources are finite, and cosmic conditions are never designed for permanence. The wonder of EC 1101 is not that it must be filled with civilizations. That would be too easy and unsupported. The wonder is that a single galaxy can contain enough stars for the question to feel almost unavoidable, while remaining so distant that the answer is completely hidden. No telescope can yet survey its planets. No instrument can detect the breath of a world there. Its possible life is a silence inside a silence, folded into starlight that began travelling toward Earth long before modern humans existed. For now, the galaxy offers a lesson in scale and restraint. It shows that habitability is not measured only by counting stars. A galaxy can be rich in suns and poor in fresh gas. It can be ancient and chemically mature, yet shaped by violent mergers. It can hold stable outskirts and dangerous centres. It can offer long-lived red stars and worlds too old to remain gentle, in the balance between abundance and adversity. I see 1101 becomes a vast field of unknown outcomes. Some planets may never have been warm. Some may have lost their atmospheres under early stellar fury. Some may orbit quietly in darkness around small stars, with the ice-covered oceans beneath their surfaces. Some may have known habitable eras that ended long ago. Some, perhaps, may still carry chemistry that has crossed the threshold into life. The statement cannot be made stronger than that. Scientific humility is part of the beauty here. The largest galaxies do not answer the question of life. They enlarge it until certainty becomes impossible and curiosity becomes calm. IK 11. 01 may be a dying galaxy in terms of star formation, but dying galaxies can still contain long-lived stars, stable planets, and hidden reservoirs of time. Inside its immense red light, the possibility of life remains neither promised nor denied, only suspended among trillions of old suns. Inside a galaxy as immense as IC 1101, the sky would not necessarily resemble the quiet night known from a small planet in the outer disk of the Milky Way. The view would depend on location, because a giant elliptical is not uniform from centre to edge. In its outer halo, stars may be thinly scattered across huge distances, and the darkness between them might feel deep and nearly empty. Nearer the core, however, the density of stars could rise until the night itself became softened by light. If planets exist in the crowded inner regions of such a galaxy, and if observers ever evolved there under stable skies, their sense of the universe might be profoundly different from one formed in a quieter spiral neighbourhood. The surrounding galaxy could fill their heavens not as a pale band, but as a broad, luminous atmosphere of stars. There might be no clear dark background against which the distant universe could easily appear. The local sky could be bright with unresolved suns, ancient red giants, compact remnants, globular clusters, and the smooth glow of the central stellar swarm. In such a place, the universe beyond the galaxy might be hidden not by a wall, but by abundance. Too much nearby light can erase the faintness of what lies farther away. IC 1101 is vast and diffuse across much of its volume, but the central regions of giant ellipticals can contain enormous concentrations of old stellar populations, and a civilization within such a region might inherit a sky shaped by nearness rather than distance. On Earth, the Milky Way is visible as a dim river only where artificial light and atmospheric haze are low. Beyond it, telescopes can detect other galaxies because the night sky is dark enough in many directions for faint distant light to stand out. In the interior of a giant elliptical, the background could be brighter, more crowded, and more confusing. The combined glow of nearby stars might create a constant celestial fog. Individual bright stars would still be visible, perhaps far more numerous than in Earth's sky, but between them there could be a diffuse radiance, a soft galactic daylight that never fully withdraws. If intelligent observers studied such a sky with early instruments, they might map a rich local cosmos and still struggle to recognize that their galaxy is only one island among many. Distant galaxies, already faint because of their distance, could be drowned by the glare of the surrounding stellar population. Dust might be less prominent than in a spiral disk, but starlight alone can act as a veil when it is dense enough. The result would be a universe that appears enclosed, not because space ends, but because the evidence of what lies beyond is hidden under the brilliance of home. This idea has a gentle echo in human astronomy, even from the comparatively open position inside the Milky Way. The nature of other galaxies was once uncertain. Some cloudy patches in the sky were star clusters, some were gas clouds, and some were separate galaxies so distant that their stars blended into faint smudges. It took improved telescopes and careful distance measurements to show that Andromeda was not merely a nebula within the Milky Way, but an independent galaxy. If that recognition was difficult from a spiral galaxy with relatively open views, it may have been harder from deep within the bright interior of a giant elliptical. The inhabitants of such a world, if they existed, might build astronomy first around their own stellar sea. They might measure nearby suns, discover clusters, infer dark remnants, and perhaps detect the central black hole through the behavior of stars and gas. Their early cosmology might treat the surrounding glow as the total structure of reality. The rest of the universe could remain invisible until their instruments became powerful enough to subtract the local light and search for faint patterns beyond it. In this way, AC 1101 becomes not only a large galaxy, but a thought experiment about perspective. A civilization's understanding of the cosmos is shaped by where it begins. A world in the outer disk of a spiral sees dark lanes, scattered stars, and enough open sky for other galaxies to become discoverable. A world near a dense galactic center may see overwhelming local brilliance. A world in the outskirts of a giant elliptical may see a dimmer, older sky with fewer blue stars and a vast central glow on one side. Each is a local window, framed by the accident of position. In IC 1101, the window could be especially deceptive because the galaxy is large enough to feel like a cosmos on its own. With tens of trillions of stars, its internal geography would contain more variety than any single civilization could easily survey. There could be dense central regions, sparse halos, ancient clusters, stellar streams, dead systems, and long-lived red stars scattered through the dark. Even communicating across a tiny fraction of such a galaxy would be limited by the speed of light. Entire histories could unfold in one region, while another remained forever remote in practical terms. A civilization inside it might not merely mistake the galaxy for the universe because of visual brightness. It might also be confined by scale. Signals crossing millions of light years would require millions of years. Shared knowledge across such distances would be impossible on ordinary biological timescales. Even if many civilizations arose in different regions, they might never know one another existed. The galaxy could contain many islands of awareness separated by distances so vast that silence would be the normal condition. The brightness of the central regions also raises subtler questions about planetary life. A bright night sky could affect climates and biological rhythms, though the effect would depend on the brightness, atmosphere, rotation, and orbit of any given world. If the background glow were strong enough, darkness might be rare. Life under such skies would not necessarily resemble life on Earth, where day and night, seasons, and moonlight have shaped evolution. On a planet deep in a luminous stellar environment, night might be more like twilight. Shadows could remain soft. The sky might be filled with a granular haze of stars, some resolved, some blended. Ancient red and yellow light could dominate, with fewer hot blue stars than in active star-forming regions. A world beneath a sky that is never fully black, surrounded by the old light of a galaxy that has almost stopped making new suns. Yet this is only one possible view. In the outer halo of a C1101, a planet might see the central galaxy as an enormous glowing presence, a diffuse oval of light stretching across the heavens, while the opposite sky opens toward intergalactic darkness. From there, distant galaxies might be easier to detect, This contrast within one galaxy shows how scale and perspective are inseparable. The same IC 1101 could be an all-enclosing sky from one world, a distant central lantern from another, and a barely visible haze from the farthest outskirts. No single viewpoint would capture the whole. For astronomy, the difficulty would be not only seeing outward, but understanding inward. A giant elliptical lacks the flat disk and spiral arms that make structure visually obvious. Its stars move in many directions, creating a smooth, three-dimensional swarm. From within, the shape of such a galaxy might be hard to infer. Observers would need to measure distances and motions across enormous volumes, distinguishing nearby stars from far ones, separating clusters from field populations, and building a model from parallax, brightness, spectra, and dynamics. The central black hole might be inferred from stellar orbits. But the full mass of the galaxy and its dark matter halo would remain challenging. They might discover gravity's hidden component through motions that visible matter cannot explain. Eventually, with enough precision, they could learn that their bright enclosure is not all there is. They could find background galaxies, perhaps first in clearer directions away from the core. They could map the cluster around them, recognizing Able 2029 not as a vague outer realm, but as a greater gravitational city. The deepest lesson of this imagined sky is that cosmic truth is not offered equally from every place. The universe can be open and still appear closed. It can be filled with galaxies and yet hide them behind local light. IC 1101, because of its scale, makes that lesson vivid. Inside it, the boundary between a galaxy and a universe might feel emotionally blurred. 100 trillion stars, ancient and softly shining, could create an apparent totality large enough to satisfy curiosity for ages. Yet beyond that light, other clusters would still exist. The cosmic web would continue. The expansion of space would carry distant systems away. The true universe would be larger than any local sky could reveal at first glance. For any mind inside the giant, discovery would require not only instruments, but the humility to suspect that even the brightest and largest home is not the whole of creation. The sky without outside would not be false, it would be incomplete. A luminous veil made by the very galaxy that gave its observers a place from which to wonder. The fate of great galaxies is rarely sudden. A star may end in a brilliant explosion if it is massive enough, or shed its outer layers in a luminous breath before becoming a white dwarf. A planet may be scarred by impact, frozen by distance, or burned by a changing sun. But a galaxy as large as IC 1101 does not die in one final blaze. Its ending is slower, quieter, and more difficult to picture, because the timescales stretch far beyond the lives of stars and the histories of planets. It fades by exhaustion. It grows older as its brightest stars vanish and fewer new stars replace them. It becomes redder as its young blue populations disappear. Its gas, once the raw material of future suns, is consumed, heated, stripped, or locked away in forms that no longer collapse easily. The galaxy remains gravitationally immense, but its power to renew itself weakens. This is the long twilight of massive ellipticals. IC 1101 stands already deep inside that twilight, not as a dead object, but as a great old system whose most fertile eras appear to be behind it. Its future is not emptiness at once, it is continuation without much rebirth, a vast persistence of old stars moving through a smooth halo, while the central black hole and the surrounding cluster environment help maintain a state in which cold star-forming gas is scarce. In that sense, EC 1101 is both a present galaxy and a glimpse of a possible future for other systems after repeated mergers have worn down their youthful structures. The Milky Way offers the nearer, gentler version of this story. It is still a spiral, still rich enough in gas to form new stars, still patterned with arms, dust, clusters, and blue regions of stellar birth. But it is not isolated from change. Andromeda is moving toward it through the local group, and far in the future the two great spirals will merge. Before their stellar disks fully combine, their dark matter halos may already overlap. Their outer stars will begin to feel the shifting gravitational field. Long tidal tails may form. Gas clouds may be disturbed and compressed. Some regions may flare with new star formation as cold gas is squeezed into dense clouds. For a time, the encounter may look dramatic from afar, with distorted arms and luminous knots of new stars. Yet the collision will not be a catastrophe in the simple sense. Stars are so widely separated that most will pass one another without direct contact. The Sun, if it still exists in a later stage of its life, may be moved onto a new orbit, but it is unlikely to strike another star. The greater transformation will be structural. The flat disks of the Milky Way and Andromeda will be scrambled. Their spiral arms will lose their old order. Their central regions will sink toward a shared remnant. Their supermassive black holes will eventually become part of the same central system. Over long ages, the merged galaxy may settle into a smoother elliptical or lens-shaped form, redder and quieter than either spiral was before. This future remnant will not be IC 1101, because the local group does not offer the same rich cluster environment. It will lack the long supply of major galaxies that helped build a central Titan in Abel 2029. Still, the direction of change is related. Spirals collide. Ordered disks are disturbed. Gas is consumed or heated. Star formation may briefly rise, then gradually decline. A galaxy that once shone with blue regions becomes older and smoother. The Milky Way and Andromeda therefore show, on a smaller scale, the same principles that may have shaped IC 1101 many times over. They also reveal that galactic fate is not fixed by internal age alone. Environment matters. In a sparse group, there may be only a few major mergers. In a rich cluster, a central galaxy may keep growing by absorbing companions and stripped stars for billions of years. IC 1101's fate is tied to its cluster, because the cluster has always been part of its identity. It may continue to accrete smaller galaxies. It may continue to gather diffuse stars from the intra-cluster light. It may experience minor mergers that add mass to its outskirts. But these additions may not restore youth. Many cluster galaxies are themselves old and gas-poor. Their stars can enlarge the giant without giving it much new fuel. Adding old stars to an old galaxy makes it larger, not younger. Even when fresh gas arrives, the central environment may heat it or prevent it from cooling efficiently. The black hole at the center may release energy during feeding episodes, stirring the gas and holding back broad star formation. The cluster's hot atmosphere may keep cold clouds from surviving. In this way, the galaxy can continue to grow while still fading in a stellar sense. Growth and aging do not always oppose one another. A giant elliptical may become more massive and more extended while its light becomes gradually older. This is one of the quiet paradoxes of cosmic evolution. The largest galaxies can keep accumulating matter after their star-forming lives have mostly passed. They become grander in size and poorer in renewal. Over much longer timescales, the fading becomes more profound. The most massive stars have already died quickly. Sun-like stars eventually leave the main part of their lives and become white dwarfs, red dwarfs. The smallest and longest-lived ordinary stars continue shining for extraordinary spans of future time, far beyond the current age of the universe. In an old galaxy, they become some of the last steady sources of starlight. The bright giants and luminous short-lived stars disappear first, leaving the dimmer stars to dominate the future. White dwarfs cool slowly. Neutron stars and black holes remain as compact remnants. Stellar encounters, rare in most regions but possible across extreme times, can alter orbits. Some stars may be ejected into intergalactic space. Others may fall inward over immense durations. The central black hole may consume occasional stars or gas clouds, but it will not devour the galaxy whole. Most of the galaxy's matter will spend almost unimaginable ages in quiet motion, not destroyed, only dimmed. The universe around it will also change. If cosmic expansion continues as observed, distant galaxies beyond gravitationally bound regions will drift farther away, their light stretched and weakened. The sky seen from within any future galaxy cluster may grow emptier of outside systems. Local bound structures may remain, but the larger universe will become harder to observe across the expanding distances. For IC 1101, this means that its future may be one of increasing isolation in a practical sense, even while it remains embedded in its cluster. The galaxies not bound to that cluster will recede. The cosmic web will become less accessible to observation from within. The central giant will remain with its companions, its hot gas, its dark matter halo, and its ancient stars, but the broader universe will slowly withdraw beyond reach. This is not the dramatic destruction imagined in some speculative endings of the cosmos. It is a dimming of connection, a deepening of distance, and a cooling of light. IC 1101's slow fading therefore mirrors the fate of great galaxies in a universe where time keeps widening the gaps. Its past was crowded with mergers, but its far future may feel quieter, colder, and more solitary. The Milky Way's future remnant will share some of that path. After its merger with Andromeda, star formation may decline as gas is used up or heated. The new galaxy will age, its brightest stars will die, its night skies, if any worlds remain to watch them, will change from spiral richness to smoother old light. The transformation will not be an ending for every star or planet inside it. It will be an ending for a form, a loss of the Milky Way as a spiral identity. That is how galaxies often die, not by vanishing, but by becoming something else, then slowly losing the conditions that once made them luminous with new birth. IC 1101 is farther along that road. It is what remains after many identities have merged and aged together. It still shines across 1 billion light years, but the light is largely the inheritance of earlier creation. In the quiet fate of this giant, the universe shows that even its most immense structures are temporary arrangements. They can last for ages beyond comprehension, but they are still chapters, not final states. The largest galaxy ever found may continue as a vast red kingdom of old suns, but its grandeur is already bound to fading. It is a monument not only to how large galaxies can become, but to how slowly even giants surrender their youth. Beyond IC 1101, the idea of the largest known galaxy opens into a wider and quieter uncertainty. The word known is doing important work, because astronomy is always limited by what can be seen, measured, resolved, and interpreted from one location inside one galaxy at one moment in cosmic history. IC 1101 may stand among the greatest galaxies ever identified, and it may remain a useful symbol of galactic immensity, but it cannot honestly be treated as the final possible size of a galaxy. The observable universe is not the whole universe. It is the region from which light has had time to reach Earth since the beginning of cosmic history, shaped by the expansion of space and the finite speed of light. Beyond that horizon, there may be more galaxies, more clusters, more enormous central ellipticals, and perhaps structures whose light will never arrive. Even within the observable region, Many galaxies are too faint, too distant, too blended with foreground light, or too difficult to classify with certainty. The largest object in a catalogue is not necessarily the largest object that exists. It is the largest that has been found under the conditions of human observation. That distinction does not make IC 1101 less magnificent. It makes the universe larger around it. Every record in astronomy is provisional, held gently until deeper surveys, better instruments, and more careful methods widen the map. There may be other cluster centers where galaxies have grown through the same processes, merging and absorbing companions for billions of years, building halos so faint that their true extent is still hard to separate from the surrounding intra-cluster light. Some may rival a C1101 in stellar mass. Some may exceed it in dark matter influence. Some may stretch broader in diffuse envelopes while appearing less dramatic in bright central light. The very act of ranking them depends on definition. A galaxy can be largest by visible diameter, most massive in stars, richest in dark matter, brightest in a cluster, or most extended through a faint halo. These categories overlap, but they do not always name the same object. A galaxy with a vast diffuse envelope may not have the highest stellar mass. A galaxy with enormous mass may not present the widest visible span. A cluster center may be so blended with surrounding light that its boundary becomes more philosophical than visual. EC 1101 lives in this complexity, and so do all candidates for cosmic record holders. The universe has not written labels around them. It has only allowed matter to gather, and left observers to decide where one structure gives way to another. This is why future astronomy may revise the story. Wide-field surveys can reveal faint outer halos. Space telescopes can detect dim structures beyond the reach of older instruments. Observations in different wavelengths can show hot gas, old stars, dust, or energetic activity that visible light alone might miss. Gravitational lensing can reveal mass through the bending of background light, even when that mass does not shine. Computer simulations can test how giant galaxies form inside clusters, showing how central galaxies grow by merging, by stripping stars from satellites, and by accumulating diffuse intracluster populations. With each improvement, the simple picture of a single largest galaxy becomes richer and less rigid. IC 1101 may remain among the great giants, but its exact size, star count, and black hole mass may be refined. Other galaxies may rise beside it in the rankings. Some may prove more massive, others may be better understood. The aim of astronomy is not to protect a title, but to understand the process behind it. The deeper question is not merely which galaxy is largest, but how large galaxies can become under the laws of gravity, dark matter, gas physics, and cosmic time. There may be practical limits. A galaxy cannot grow without an environment that supplies material. It needs nearby companions, a deep gravitational well, and enough time for mergers to occur. In a sparse region, even a massive galaxy may have few opportunities to become an extreme central giant. In a rich cluster, growth is easier, but not unlimited. Fast-moving galaxies may pass through the cluster core without merging. Gas may be stripped and heated rather than added as cold fuel. The cluster's own identity may begin to dominate over the central galaxy's identity. At some point, adding more diffuse stars may enlarge an outer envelope while making the boundary less meaningful. There may also be limits connected to black hole feedback, because an enormous central black hole can heat surrounding gas and reduce future star formation. Growth can continue by adding old stars, but the formation of new stars may remain suppressed. Thus, the largest galaxies are likely not endless factories of light. They are vast collectors, shaped more by the inheritance of other systems than by ongoing creation. The cosmic horizon adds the final uncertainty. The observable universe may contain enough examples to show the broad range of galaxy sizes, but it cannot reveal what lies beyond the region whose light has reached Earth. If the larger universe extends far beyond what can be observed, then it may contain many more galaxy clusters, including rare regions where matter gathered in especially favourable ways. There could be central galaxies larger than any now catalogued, not because they break known physics, but because an even larger sample allows rarer outcomes. On Earth, finding one extreme object within a limited survey does not prove that no greater one exists elsewhere. It only shows that the universe can produce at least that much. IC 1101 is therefore both a summit and a signpost. It stands near the top of current knowledge, while pointing beyond itself to all that current knowledge cannot include. Its light has crossed 1 billion years to reveal one enormous central galaxy, but there are reaches from which no light will ever be received. In that darkness of distance, there may be giants unseen, galaxies whose histories are as rich and old as IC 1101, or older, or stranger in ways that remain inaccessible. This is not a reason to invent false certainties. It is a reason to let the unknown remain wide. The most beautiful form of speculation in science is not the claim that anything imaginable must exist. It is the recognition that known processes, given enough space and time, may produce outcomes larger than those already measured. Gravity has built galaxies from small beginnings. It has drawn clusters into dense nodes of the cosmic web. It has allowed central ellipticals to grow by swallowing the remains of their neighbours. Nothing in this story suggests that human catalogues must have already found the ultimate example. At the same time, known physics gives the speculation shape. The unseen giants, if they exist, would still be governed by gravity, dark matter, gas, star formation, black hole feedback, and the expansion of the universe. They would not be magical exceptions. They would be rare consequences of familiar rules playing out in rare environments. IC 1101 remains powerful because it is close enough in cosmic terms to be studied, distant enough to feel ancient, and large enough to press against the limits of intuition. It shows that a galaxy can become a region almost comparable to a galactic neighbourhood, a diffuse empire of old stars extending through spaces where smaller galaxies might otherwise stand apart. It shows that the history of collisions can create calmness, that the aftermath of violence can look smooth, that growth can lead not to youth but to red and quiet age. Its outer boundary fades into ambiguity. Its central black hole hides behind distance and light. Its star count rests on inference, and its record rests on definitions that may change. Yet these uncertainties do not diminish the object. They make it more faithful to the real universe, where the largest things are rarely simple. A sharp number is easy to remember, but a blurred boundary is often closer to truth. As the frame widens beyond IC 1101, the galaxy becomes part of a larger meditation on measurement itself. Human astronomy measures the universe from within the universe, using light that is delayed, stretched, filtered, and incomplete. Every distant galaxy is seen as it was, not as it is at this present cosmic moment. Every edge is partly a decision. Every mass estimate depends on models of what cannot be directly touched. And still, from these fragments, a coherent story emerges matter-gathered, stars formed, galaxies merged, clusters grew, and in some cluster hearts, giants rose. IC 1101 is one of those giants, not the end of the story, but one of its clearest and most humbling chapters. Beyond it, deeper fields of space continue, carrying unknown numbers of galaxies into darkness and distance. Some may be smaller than any yet known. Some may be faint remnants barely holding their stars. Some may be immense red ellipticals at the centres of clusters whose light is still crossing the void. The largest galaxy ever found is therefore also an invitation to think about all galaxies not yet found, and all the cosmic history that remains outside the reach of present sight. In the silence beyond the measured edge, there may be no final champion, only a continuing hierarchy of vastness, where each discovery widens the question and leaves the universe larger than before. The story of SC 1101 settles at last into silence, not because the questions are finished, but because the scale has widened beyond the reach of any final answer. A galaxy of such size is not only an object in space, it is a record of gravity working patiently through deep time, drawing smaller systems together, reshaping their stars, dimming their youth, and leaving behind a broad red glow at the center of a distant cluster. Its light carries the memory of collisions that no living mind has seen, of star fields blended beyond recognition, of black holes growing in darkness, and of ancient suns continuing to shine long after the brightest fires have faded. Around it, the universe remains larger still. Other clusters drift in the cosmic web. Other galaxies wait in distances not yet fully measured. Beyond the observable horizon, light has not arrived and may never arrive, leaving the greatest structures of all suspended outside human knowledge, yet even within what can be seen. I see 1101 is enough to soften certainty. It shows that grandeur can be quiet, that violence can become smoothness, and that the largest things may fade with the same patience that formed them. The Milky Way continues its own slow journey, bright with younger stars, moving toward its future merger, carrying within it worlds, dust, gas, and all the small local histories that make a galaxy feel like home, far away. IK 1101 remains a deeper mirror of what time can do when gravity is given enough matter and enough darkness. Its vastness is not an ending, but a calm reminder that the universe is still unfolding in scales beyond instinct, beyond sight, and beyond any single name. The final image is not of a record holder, but of old starlight crossing space, faint and steady, arriving after 1 billion years with a quiet message that even giants are temporary, and even temporary things can be immense,